Welcome back, everybody. AP Chemistry. This is Unit 6, Section 3, taking a look at how the pressure of solutions will interact when we add in and be affected when we add in different solutes of different types. Okay, so basically we've got two ways of describing this and the interactions therein. The first way is through Raoult's law. This describes that the presence of a non-volatile solute will lower the vapor pressure of the solute, of the solvent itself. So here's what we mean by that. If I've got just a flask, okay, and in that flask is going to be just water, okay, so plain old water, and at room temperature, it is going to evaporate up, isn't it? We're going to lose some of that to the atmosphere. Well, if I add particles to it, what's going to happen is it's going to stick to those water molecules and limit the amount of pressure that we find inside the flask. And when I say pressure, envision this being closed off or anything like that, but the rate at which it's going to be going up into the atmosphere. That's Raoult's law describing that relationship. And so there's a math way to be envisioning with this, and so Raoult's law says this. The pressure of the solution is going to be a function of the mole fraction of your solvent times the pressure of the solvent itself, the vapor pressure of that solvent. Okay, so that's basically Raoult's law as it works with that. And so we are going to be taking a look at the interactions at equilibrium of the pressure of a liquid in with its vapor. So as you add energy, the liquid is going to go to vapor, and as you take the energy away, the vapor goes back to liquid, and so on. Okay. Now, boiling liquids are dependent upon the equilibrium vapor pressure. This is an illustration of Pascal's law. So here's what I mean by this. If I take a flask and I start to boil it up, let's say I put it at 100 degrees Celsius. Okay. We know that water boils at 100 degrees Celsius. That's under standard conditions. So 760 millimeters of mercury will give me a 100 degrees Celsius boiling point. Okay. But if I don't have 100 degrees Celsius, or I don't have an atmospheric pressure, let's say I increase the pressure. Let's say I go to 800 millimeters of mercury. Pascal's law says as you add energy or add pressure pushing down on this, it's really hard for those particles to actually escape up. They're pushing against one another. So if I add pressure to it, what ends up happening is water won't boil until I get to something like 110 degrees Celsius. Now, if I go somewhere like Denver, where I have less atmosphere, say I have instead like 525.8 millimeters of mercury. If I have less atmosphere pushing down on there, a smaller force, well, it's easier for these things to push against. And so my boiling pressure, if I was somewhere like that environment, would be down to 90 degrees Celsius. Okay, so that's just the interactions between the atmospheric pressure pushing against the solution itself as it's trying to vaporize. All right, so let's take a look at some problems and how this might be applied. All right, we're going to calculate the vapor pressure for a solution that's prepared by dissolving some solutes into some particles of things into my solution. So envision this, that I've got my flask and I've got some water in here, and it tells me that I have 643.5 cubic centimeters of water. Okay, now I'm going to be putting in let's see, 158 grams of sucrose or table sugar. Okay, remember that the pressure of the entire solution, the water is going to try to evaporate up. I want to know the pressure of my solution. That's going to be a function of my mole fraction of water times my vapor pressure of water. Okay, so notice I've got to find my mole fraction. So I have to convert my 158 grams of sucrose into moles. And so that's going to be a rate of 342 grams per mole. And this is going to give me 0.462 moles of sucrose. Okay? Now for my water. Now be careful, because we typically would say, 1 cubic centimeter of water is 1 milliliter. And if it's pure water, distilled water, that would be 1 gram. But they tell me that it's not pure water because they give me the density. So I have 643.5 cubic centimeters of water, and the density of this water is 1 cubic centimeter is 0.9971 grams. Okay, must not be pure water. So that will give me 641.6 grams of water. Now, I want to find a mole fraction. Don't lose track of what we're trying to do here. 18 grams of water, and I want to convert that to moles. And so this ends up being 35.6 moles of water now. So the mole fraction of my water is 35.6 moles of water. Keep track of what we're doing. Divided by the sum of the two moles. So I have 35.6 plus my 0.462. All right. And so I end up in this case having a mole fraction of 0.987. Okay. So 0.987 goes here. And my vapor pressure of water was something called 23.76 torrs. Pressure can be in kilopascals, can be in torrs, can be in atmospheres or whatever. And so if I just multiply the two, I end up with a value of 23.45 torrs. That's the pressure of the solution. Now, did Raoult's law apply? Remember, as I add particles to this, we should see that the vapor pressure, or the pressure of the solution, should go down. And yes, it went from 23.76, now we're at 23.45. So there's Raoult's law. Now, let's take a look at another example. This example includes two liquids. And so this is a little bit different, because inside this solution, inside this flask, I find two liquids now. So I have my butane, and I also have my octane. And so I've got both of them wanting to go up. Okay? And so it's a little bit different scenario, because Dalton's law of partial pressures says that the pressure of a solution, and this is of two gases now, is going to be the sum of those two. So it's the sum of butane and my octane. Okay? So how do we figure out those pressures? Okay? Well, we got to figure out those pressures the same way, but I have to find my mole value. So I have to find my pressure here and my pressure here. Okay, so let's take a look and let's break this down. Let's look at octane first. Okay, my octane, I had 10 milliliters of it, and we had 1 milliliter is 0.75 grams. That's its density. And so I ended up with 7.5, I should say, grams of octane. Converting that into moles, 114 grams per mole is going to give me 0.066 moles of octane. Okay, I'm going to label up everything here because we're going to have to do some math with both of these because they're both going to become gases. So 15 milliliters of my butane now has a different density. So I have 1 milliliter is 0.98 grams. And so I end up with 14.7 grams of butane. Let's convert that into moles. So 58 grams of butane is 1 mole. And so I end up with 0.25 moles of butane. Okay, so let's find my, if I'm going to be figuring out my pressure of my different gases, let's do the pressure of my octane first. To find my pressure, I have to find my, my mole fraction. So let's find my mole fraction of my octane by taking the 0.066 moles of octane divided by the sum of those two, 0.066 plus my 0.25. My mole fraction of octane is 0.209. Now my mole fraction for my butane, I could just subtract from 1, but if I do the math part, it's 0.25 divided by 0.066 plus 0.25. I'm going to end up with a mole fraction of 0.791. And again, that's of my butane. Once again, these two should add up to 1 or really close to that. So if I want to find the pressure of the entire solution, that's the first step. I'm going to take a look at my mole fraction. I'm going to take a look at my torrs, and I simply add those up. Okay, so the pressure of my solution, in this case, I had in my butane, let's see, that was a 0.791. And I had 100 torrs on that one. And over here, I had 0.209 times my 150 torrs. Okay, let's see, was that 150? Yeah, here it is over here. 150 torrs. So the pressure of the solution ends up being 110.45 torrs. Okay, I add those up. Now I'm gonna cheat for the next problem just a little bit because if I do this, I'm going to end up with let's see, this is 31.5 torrs. If I multiply, this is 31.5, and this ends up being 79.1, doesn't it? Okay, I'm just setting up the case for the next problem. Let's take a look now at the mole fraction of the two gases in the vapor. Okay, now be careful. I want to know the mole pressure of the gases in there. So my octane, remember I had those two together, the pressure times my mole fraction, that ended up being 31.35 torr. That's going to equal the mole fraction of my octane times, right here, there's the pressure of my solution, 110.45. So my mole fraction ends up being 0.284. That's the mole fraction of my octane. Okay, now let's do the same thing for my butane. Okay, my butane, again, I kind of cheated because I knew it was coming, so I just multiplied this ahead of time. My mole fraction of my butane is going to be my 79.1 times my pressure of the solution was 110.45. That equals 0.716. Okay? So that's how I find those from that if I knew the pressure of the entire system. The pressure of the gas is going to be the mole fraction times the pressure total. Okay? Because I can mix and match this equation. All right. Last problem. If I take a look at it this way now, predict the vapor pressure of a solution. So we're predicting that pressure. Remember that the vapor pressure of my solution, the pressure of my solution is a function of the mole fraction of my water times the pressure of my water, because that's the solvent that we're working with here. Okay, we're putting 35 grams of sodium sulfate into a certain number of grams of water. Okay, so let's find my water first. Again, this is the real problem when I deal with this problem, is finding my mole fraction. So let's deal with my water first. Okay, so water, we have 175 grams. And 18 grams of that per mole, I end up with 9.72 moles of water. Okay, let's do the same thing now with my sodium sulfate. We're given 35 grams of that, and the formula mass of my sodium sulfate is 142 grams per mole. That gives me 0.246 moles of sodium sulfate. Now we got to be clever here, because remember, this is an ionic compound. I have 2 sodium ions and 1 sulfate ion. So all the others were non-volatile, weren't they? They acted as 1 particle. But here, this acts as 3 particles. So I'm not quite done. I have 2.246 moles of this, but I have 3 particles. Okay? So it's kind of like a Van 't Hoff factor in here. And so what I end up with is 0.738. Okay? Now, what do I do with this? Let's find my mole fraction of my water. 9.72 moles of water. And that we're going to divide that by 9.72 plus my 0.738. And so I end up with a mole fraction of water of 0.929. Okay, so 0.929 goes here. My pressure of my water was 23.76 torrs. So 0.929 times 23.76, that will give me 22.1 torrs. Okay? Raoult's factor says that as I add particles in, it's going to decrease that pressure. And since I had 3 particles, that's the key to unlock this, is taking a look at the ionic nature of this having 3 particles. Okay, so that should be pretty much all you need to do the next set of problems. And just keep track of those different things of the mole fractions and so on. You should be good to go. Okay, problems 1 through 4. Good luck to you guys.